Beneath a crust of ice tens of kilometers thick, on a moon with no air and surface temperatures colder than Antarctica in winter, there may be more liquid water than in all of Earth's oceans combined. And that ocean has been stable for billions of years, bathed in energy, rich in chemistry, completely hidden from sunlight. If you were looking for life beyond Earth, you might expect to look at Earth-like planets. But some of the most promising habitats in the entire solar system are not planets at all. They are frozen moons. And one of them, Europa, is whispering a tantalizing possibility that we are not the only ocean alive in the dark. Europa is one of Jupiter's 4 large Galilean moons, discovered by Galileo in 1610. It's a little smaller than our own moon, about 3,100 kilometers across, orbiting Jupiter every 3.5 days. From the outside, Europa looks deceptively simple, a smooth, bright, almost featureless ball of ice, crisscrossed by long reddish-brown fractures. There are almost no big impact craters, which tells you something important. The surface is young and constantly being reshaped. That's weird. Airless, icy worlds are supposed to be geologically dead. Something inside Europa is active enough to erase scars and redraw the surface over tens of millions of years. Those long lines you see are called lineae, fractures where the ice crust has stretched, broken, and shifted. Around them, you find chaotic terrain, jumbled blocks of ice that look like they've been broken, rotated, and refrozen. The best explanation is that Europa's outer shell is a floating ice lid, maybe 10 to 30 kilometers thick, riding on top of a global ocean of liquid water. Underneath that, Europa probably has a rocky mantle and an iron core, like a small terrestrial planet. So this is the basic picture. Rock at the bottom, water in the middle, ice on top. A complete ocean world orbiting a gas giant 780 million kilometers from the sun. But how do we know that ocean is really there if we've never drilled through the ice? The evidence comes from several independent lines of physics. First, Europa's density, about 3 grams per cubic centimeter, tells us it's mostly rock and metal, with a layer of water and ice roughly 100 kilometers thick. Second, when the Galileo spacecraft flew past Europa in the late 1990s, it measured how Europa moves in Jupiter's gravity. The way the moon flexes and responds suggests a decoupling between the outer shell and the interior, exactly what you'd expect if there's a liquid layer. The clincher came from Galileo's magnetometer. Jupiter has a powerful magnetic field, and as Europa orbits, that field sweeps through the moon. Galileo detected an induced magnetic field inside Europa, a secondary field generated when a conductor moves through a changing magnetic environment. On Earth, that conductor is our molten metal core. On Europa, the simplest explanation is a global shell of salty, electrically conductive water, at least tens of kilometers deep. Later, the Hubble Space Telescope spotted hints of water vapor plumes erupting from Europa's surface. If those plumes are real and persistent, they may be tiny leaks from that hidden ocean, venting into space. So Europa almost certainly has a deep, salty ocean. But liquid water needs energy to stay liquid, especially this far from the sun. At Europa's distance, sunlight is only about 4% as strong as at Earth, not nearly enough to melt a global ocean. The key is tidal heating. Europa orbits very close to Jupiter, locked in a gravitational dance with 2 neighboring moons, Io and Ganymede. Their combined tugs keep Europa's orbit slightly elliptical. As Europa moves closer and farther from Jupiter each orbit, Jupiter's gravity flexes the entire moon, squeezing and stretching it like a stress ball. That constant flexing generates frictional heat inside Europa's rocky interior and its ice shell. It's the same process that turns Io into a volcanic hellscape, but dialed down. Models suggest this tidal heating can supply more than enough energy to keep a global ocean from freezing solid over billions of years. Some of that heat will be concentrated at the seafloor, where rock and water meet. On Earth, that's exactly where we find hydrothermal vents, cracks in the ocean crust, where hot, mineral-rich fluids gush out, powered by internal heat, not sunlight. If similar vents exist on Europa, they could be engines for complex chemistry and potentially biology. On Earth, hydrothermal vent ecosystems are astonishing. At places like the Mid-Atlantic Ridge Entire communities of organisms live in complete darkness, kilometers below the surface. They don't use photosynthesis. Instead, they use chemosynthesis. Bacteria harvest energy from chemical gradients, like hydrogen sulfide mixing with oxygenated seawater, and build organic molecules. Larger animals feed on those bacteria, forming a full food web, all powered by geology. This is crucial for Europa because sunlight barely penetrates even a few meters of ice, let alone tens of kilometers. If life exists there, it almost certainly relies on chemical energy, not light. For life as we know it, three ingredients seem essential: liquid water, a source of energy, and a supply of chemical building blocks. Carbon, nitrogen, phosphorus, and so on. Europa's ocean checks the first box in spectacular fashion. Tidal heating and possible hydrothermal activity check the second. What about chemistry? Spectra of Europa's surface show salts and possibly sulfur compounds mixed into the ice. Radiation from Jupiter's magnetosphere slams into that ice, breaking apart molecules and creating oxidants like hydrogen peroxide and oxygen. If those oxidants can be transported downward through cracks, convection, or slow overturning of the ice shell, they could mix with reduced chemicals from the rocky interior, creating powerful energy gradients. That mixing of oxidants from above and reductants from below is exactly the kind of disequilibrium life loves to exploit. Some models suggest Europa's ocean could have as much chemical energy available per square meter as Earth's deep ocean floor. It might be enough to support microbial biospheres or even larger, multicellular organisms, though that's much more speculative. The ocean's depth, perhaps 60 to 100 kilometers, also means enormous pressure at the seafloor, potentially hundreds of megapascals. But pressure alone doesn't forbid life. Microbes on Earth thrive in deep trenches under similar conditions. The bigger question is time. Has Europa's ocean been stable long enough for life to originate and evolve? We don't have a time machine, but we can send robots. The next big mission is NASA's Europa Clipper, scheduled to arrive in the early 2030s. Instead of orbiting Europa directly, it will orbit Jupiter and swoop past Europa about 50 times, each flyby skimming as low as 25 kilometers above the surface. On board, a suite of instruments will map the ice shell, measure the thickness of the ocean, sniff the tenuous atmosphere, and crucially, sample any plumes it can fly through. If water vapor jets are spraying material from the ocean into space, Clipper can taste that spray without ever landing. By analyzing the mass and charge of particles in those plumes, Europa Clipper can look for salts, organic molecules, and complex chemistry. A magnetometer and gravity measurements will refine our picture of the ocean's depth and salinity. An ice-penetrating radar will probe the crust, searching for pockets of liquid water closer to the surface, potential lakes trapped within the ice. The European Space Agency's JUICE mission, already on its way to Jupiter, will also study Europa from a distance before focusing on Ganymede. Together, these missions will turn Europa from a blurry, mysterious moon into a well-characterized ocean world, and they will tell us how habitable that ocean really is. The ultimate dream, of course, is a lander, a machine that could touch Europa's surface, drill or melt a short distance into the ice, and directly analyze what it finds. Even without reaching the ocean, a lander could study fresh material thrown up by recent fractures or deposited from plumes. It could search for complex organic molecules, measure isotopic ratios, and look for patterns, like specific combinations of amino acids or lipids that are hard to produce without biology. Going deeper, all the way to the ocean, is a far future challenge. You'd need to get through tens of kilometers of ice, sterilize your probe to avoid contamination, and somehow send data back through the frozen shell. So we stand at a threshold. We know Europa has a vast, salty, probably long-lived ocean. We know it has energy sources and interesting chemistry. What we don't know, and what may be one of the most profound questions in science, is whether that ocean is just water and rock, or whether it has crossed the line into biology. Is life a rare cosmic accident that happened once on Earth, or a natural outcome whenever you give the universe liquid water, energy, and time? Europa is one of our best chances to find out. Until we do, it remains a silent, glittering question mark orbiting Jupiter, waiting for curious minds like yours to keep wondering, and for missions like those we follow here on Terra Nova to go and ask.